Hi everyone, welcome to this video series where we are talking about KNN and the concept of neighbors algorithm, detailed explanation of some of the considerations used in KNN, and a comprehensive coverage on model evaluation techniques. So in this particular video, we'll talk about the evaluation techniques. In the previous video, we talked about the context of KNN, choosing the right number of neighbors. How do we break the ties when it comes to samples or neighbors at equal distances? How scikit-learn addresses the tie situation. We also saw the importance of scaling in KNN and handling of categorical data and numerical data together. In this video, we'll talk about the model evaluation technique used in any typical machine learning or deep learning. Let's get started. The model evaluation techniques while using KNN, and I'll be talking about the metrics, classification metric in this example, learning curve, and cross validations. So welcome again to this video. In this video, we'll explore various evaluation metrics, especially for classification, learning curves, and cross validation. Essentially, these classification metrics, for example, performance of a KNN model involves assessing the ability to correctly predict the class labels when we use the test data. Common classification metric that we use are accuracy, precision, recall, F1 score, and confusion matrix, to name a few. Learning curve is used to understand how a KNN model performance evolves with increasing amount of training data. This is essential. And learning curve gives us with a visual representation like a plot, and that demonstrates the relationship between model's performance and the amount of data used in that particular iteration. And cross-validation techniques such as k-fold and many variations of the k-fold, like stratified and a repeated k-fold, they allow for a better understanding of the model performance in general. So let's get started here with some of the metrics. So confusion matrix. So let's say you have the actual labels in white S and predicted labels in white red, and some of the positions where the model is making an error in prediction. For example, here the class of 1, it is being predicted as class of 0, and so on and so forth. So there are some places where it is making an error, and the other places it is doing a perfect prediction. So we can compute the confusion matrix by using scikit-learn package, and it will produce an output like this. So the way to read this output is all the diagonal elements are correct predictions and the non-diagonal elements are incorrect predictions. For example, here the breast cancer data set. Let's say we have malignant samples, and there are 43 of them total. Out of 43, 8 are correctly predicted, 5 are wrongly predicted, and benign samples are 71, and all are correctly predicted. That's how we read the confusion matrix. So accuracy is simply the diagonal elements. So let's like this, the diagonal elements, count the number of diagonal elements, divide by the total number of samples will give you the accuracy. Error rate is just the opposite, which is 1 minus the accuracy rate. Okay, so that's the basic definition. And scikit-learn also provides another function called classification report. And this pretty much reports your accuracy that we just saw, along with the number of samples used in the testing. For example, malignant and benign samples, and total 114 samples. It reports the accuracy. Along with that, it reports recall and precision, and some variation of the precision and recall, the macro and weighted macro. So let's look at each one of them. The precision is the accuracy of positive predictions made by the model. Recall measures the ability of the model to capture all the positive instances as positive. F1 score is a harmonic mean of precision and recall, useful when we have imbalanced data set. Support is simply the number of samples we use in the prediction test. Accuracy is overall accuracy. Let's look at each one of them. Recall is about each class. Say, for example, this class, total number of samples is 4, and out of that, 3 are rightly predicted. So the recall is however many are right predictions divided by the total number of samples. So that's called the recall or sensitivity or true positive rate. So for breast cancer data set, we have two classes. If you recall, we have two classes, benign and malignant. Benign is a negative class and malignant is the positive class. That means the cancerous sample. This is how the confusion matrix probably will look like with some numbers here. So on the diagonal side is the number which are true and correct predictions. For example, class 0, which is benign, recall here would mean the number of samples here 6, and out of that 4 are right predictions. So the recall is going to be 4 over 6 for this particular class. And likewise, for class of 1, which is malignant, down below, and here 3 over 4. That's the recall for class of 1. So in case of multi-class, how do we compute? Let's say we have three classes, A, B, C, and these are predictions. And we simply look at the class here and the right prediction here, 20 by 27 here. And for class B, is going to be 18 by 22. So that's the recall for B. And similarly for C is going to be 15 by 18. That's the recall for the class C. That's how we compute for multi-class. Now the some of the weighted average and macro and micro variations of the recall. So for example, again, let's take a look at the actual ABC and the predicted ABC classes. So total positives here count, which is the diagonal element, divided by the total number of samples. That gives you the recall here, total number of samples here. So that gives you recall, and you can compute the recall by using the recall score, pass the labels, actual and predicted, and also pass the method called micro. So the other variation is macro, which is about recall for every class. So you compute the recall for every class and then average them. That can be easily computed by using recall score, labels, actual and predicted, and pass the argument macro. Weighted average is slightly more interesting. In this case, we look at the proportion of data in the test sample for A, B, C, and based on the proportion is going to generate a weight, and scikit-learn will do it behind the scene for us. Let's say the weight is 3, 3, 3 each. So we're going to multiply the recall of A with 3 and recall of B with 3 and the recall of C with 3 and divide by the total sum of the weights for normalizing. So using this line of code, you can get the weighted average of the recall. Precision, on the other hand, is about the number of positive samples that the model has predicted, and we would like to get the high true positive and 0 false positive. That's the objective here. So for breast cancer data set again, let's say this is for breast cancer again, I mean here true positive and false positive, and then the ratio is going to return the precision. As low the false positive is good for the model. So precision in the multi-class again. So now things we have to look at uh, from the prediction angle. And here the total number of prediction 20 and divided by all the predictions. So that is precision of class A, precision of class B and C. And likewise, we can compute the micro, macro, and the weighted precisions as well. Now, precision and recall typically have inverse relationship. High precision means somewhat lower recall by nature. So let's see why that is so. For example, we compute the precision and recall for this data set, and we use simple formulas to compute the precision and recall. Getting high precision and recall is the objective, but it's not possible to get a true one for precision and a true one for recall because of the nature of the opposite nature of precision and recall. So let's understand how we get the high precision. Let's say high precision means lower false positive and as many true positive as possible. That means you want the model to say a sample is positive with a very high confidence, and high confidence means the high probability. So with the high probability, you're telling the model that predict the sample as positive only when the prediction probability is very high, let's say 0.09. So when the probability is 0.09, we say the model is that sample is malignant, otherwise benign. Malignant is class of 1, benign is class of 0. Let's take some example here. Let's say this is your data set and we're going to take one sample at a time. Imagine the first sample we took was a benign, class of 0, and the prediction probability is 0.65, which is lower than 0.9. So that remains benign, and that's the true negative. Let's talk about another sample, malignant with positive and class of 1. Let's say the model predicts 0.35 and 0.65. So this is positive, but 0.65 is not more than 0.9. So we're not going to say this is malignant. Instead, we're going to say this is benign, and that's going to be false negative. And likewise, we take the third sample, and this is positive and 1. And here the probabilities are 0.15 and 0.85. And again, 0.85 is lower than 0.9. And that means it's benign as well. And that's false negative. And likewise, one more sample here, malignant, positive 1. And the probability is 0.05, 0.95. Now this is more than 0.9. So we will say this is malignant, which is okay, this is true positive. Take one more sample here, 0.39, 0.69. 0.69 is less than 0.9. So that's not positive. So we cannot say this is malignant. So we are going to say this is benign. And that's false negative. So the pattern that you see here is with a high cutoff, we are going to say this is malignant only when the probability is really, really high. And that's 0.9. Otherwise, even some of the positive samples can turn false negative. So your false negative is increasing, but the false positive is very controlled and limited. So the result is here the high cutoff for positive cases, we have fewer false positive, but at the same time, the false negatives are increasing. So if you look at it, the precision is about true positive and a false positive, and false positive is reducing. True positive is true positive only when the model is very, very confident. That means they are absolutely true positive, and hence the high precision. So due to the high cutoff, the true positives are really confident, and false positives are very, very less, very, very low. So that ends up in a high precision. That's what we want. But on the contrary, or on the flip side, what we get is recall, which is affected by false negative, and false negative is increasing. So the denominator is increasing and hence the recall is decreasing. And so recall is low. So that's the situation or relation between precision and recall. High precision invariably will give you a low recall. And vice versa. Let's say when you want a high recall, means all the samples that you have in the actual should be predicted correctly. In that case, we go with a lower threshold here for saying a malignant sample, for example, as malignant, go with a lower sample. So a lower probability. So what will happen in this case? Let's take a few examples. Let's say first sample, the negative, that means it is benign, and the probability returned by the model is 0.325, which is lower than this. That means that remains benign, and that's true negative. Second sample is positive in the data set, and the probability is 0.65, which is more than 0.35, and that is malignant. That's also okay because the sample was positive anyway, so now prediction is also positive. Next one is benign, which means is negative, and the probability is 0.44, which is more than 0.35. So now this will be turned into malignant because the probability is more than 0.35, and that's false positive. So with this, we are increasing the false positive. Another sample with the negative here, and this is actually negative, but the probability return is 0.95. That means this is definitely going to be malignant, and hence the false positive count. So if you notice here, the false positive counts are increasing because of the lower threshold. So the result of this is with the low cutoff of 0.35 for positive, we end up having more false positive and lower false negative. So the effect is the precision, which is impacted by the false positive in the denominator, which is increasing, hence lower precision. On the flip side, or on the other side, here recall, the false negatives are, lower. In that case, the recall is getting high. So in this situation, you have the opposite behavior. Recall is high, but the precision is low. And that's why in machine learning, we need to strike a balance between precision and recall. Let's take a look at the sample Python code to understand the behavior of precision and recall. Let's take a look at a simple example here of metric. I'm going to use the breast cancer data set along with the model KNN and the confusion matrix and accuracy score. So load the data, put it in a data frame, split into train type split, and then the model default settings. Fit the model with this data, and then predict. So when you predict, you get the results in terms of the labels. And confusion matrix is simply computed by using scikit-learn computer confusion matrix. You can plot it here. So the way to read that is diagonal are right predictions and these are wrong predictions. So that's how we read the confusion matrix. The accuracy score, again, you have to pass the actual label and predicted label, and that's the accuracy score. Classification report, here each of the element here. So number of samples for testing. And the overall accuracy is here. We also talked about individual class recall, and we spoke about the macro and a weighted average. So the classification report is like one function which reports almost everything here. You can also get the micro and macro and weighted average by using precision score function and recall score function for recall here. So that was a quick demo on metric. Let's understand the PR curve. So here in the PR curve, I'm going to use the load breast cancer data set. And this is a little function to compute the precision and recall for a given pair of arrays, and the arrays are actual label and the predicted labels. So you need to pass that here, actual labels and predicted labels, and that's going to compute the precision and recall. So load the data here and train test split and train the model and predict. And you can test out here the function that you wrote earlier. This is my precision, this is my recall. Okay, so now in order to simulate the precision recall curve, we need to simulate various probabilities, and that probability will be used to compute the precision and recall for each of the probabilities. For example, let's say we take the starting probability 10%, so that means any prediction which is more than 10% will be considered as class of 1 or malignant. Similarly, I'm going to increase that probability cutoff by 5%, so the next cutoff will be 15%. That means if the prediction probability is more than 15%, that means the prediction is going to be malignant. So likewise, you're going to do that for each of these probabilities. And for each probability, we're going to ask the model to compute precision and recall. So, and then when you plot, we get a curve like this. And as you see here in this plot, it's obvious that high precision and high recall, let's say high precision would be this point and high recall is also this point, which is not possible. So in this data set here, you can go up to the precision of this and recall of only up to 0.8 or something. So there is a trade-off. Similarly, when you get a recall of 1, then you get a precision of 0.9. So there is a trade-off here. So this trade-off needs to be analyzed, understood, and discussed within the team. And then we make a decision of what should be the cutoff for probability. I hope this demo is easy to understand. So that was a quick demo on precision recall and the PR curve. Let's talk about another evaluation technique called cross-validation. So cross-validation is used for assessing, various combinations of the data, like training and testing, and perform the repeated training and testing and do the average over all the repetitions, and calculate the overall accuracy. So this returns a kind of a robust understanding of how the model generally performs across the data that we have in the data set. Typical cross-validation methods are k-fold cross-validation, where we are dividing the data into 5-fold. Stratified means we are going to consider the labels, distribution of the labels as proportion, and then that stratification will be retained in the fold. Leave one out is a one sample being kept out from the training set, and then train the model with the remaining data and just one sample for testing. And this will be repeated for all the samples in the data. Some more variations: shuffle split, where you're shuffling the data and then training it and then testing. Stratified shuffle split, which is variation of shuffling and stratified sampling. Repeated k-fold is the same k-fold but repeated a couple of times or 3 times or 4 times as you want. Those are configurable parameter. So let's see the Python code for this. So again the data set is cancer data set, a neighbors classifier, and some of the cross-fold method, cross-validation method, like stratified k-fold, leave one out, shuffle split. These are all part of model. selection package. So load the data, and one by one you can perform here. Let's say I'm going to use k-fold. So we have to use k-fold within the cross-validation score function, and that's going to return the overall accuracy, the mean accuracy using k-fold. Similarly, stratified k-fold, that is another function argument passed to the cross-validation score, and that's going to return the score as 92 and 91, pretty much the same, right? Leave one out, cross-validation, mean one sample being kept out. Again, cross-validation score, and leave out one sample at a time. And this will be repeated for as many samples you have, and you get a score of 92. So now you see here pretty much this score is consistent by using different cross-validation techniques. Shuffle split is shuffling the data first and then splitting it. So that's called shuffle split. And we want 5 splits after shuffling. So let's apply the shuffle split. And again, you get pretty much in the same line. Stratify shuffle split, again, a variation of the same. We use stratify shuffle split as a splitter. And you notice pretty much in the same range here. And repeated k-fold is a k-fold, but repeated a few times. And let's say I want to repeat 2 times or 3 times, depending on the need. And all the cross-validation methods establish the fact that the model is pretty robust with this particular data. So the cross-validation tells us that we can go ahead with this particular model, with this configuration, with this data for our production setup. So that was the demo on the cross-validation methods. Now, cross-validation methods can also help us detect overfitting in the model, if the model is actually overfitting. So slight variation again, and there is a scikit-learn package called cross-validate to do so. The idea is to ensure the accuracy that is coming from the training set and the testing set are pretty much in in similar range. There should not be a huge gap, like training accuracy of 90% and 60% being the testing accuracy. So that will give us an intuition that the model is good with the training data, but not very good with the testing data. And there is a gap, and that gap is called overfitting. So let's take a look at the sample code again. So again, the load, breast cancer data set and splitting model cross-validation score. You can do cross-validation score only on the training set and see the result, or only on the testing set and see the result. Now, this may not be the right approach to do it. The correct approach is to use the cross-validate function. Use the cross-validate function, provide the model, provide the data, X and Y, and choose your cross-validation, let's say 5-fold or 8-fold or 10-fold, and a scoring technique, whatever scoring technique we want to use here. Now we can mention multiple scoring methods like accuracy, precision, recall, and all of that. That's the advantage with cross-validate. Then you tell cross-validate to test the model using the training samples also. So the result will be for each fold is going to do the testing against the training set and testing against the test set. So you notice here test accuracy and train accuracy, test precision, train precision, test F1, train F1. And then you can plot them to see if they are in the similar range or not. This is how we detect overfitting in the model, or one of the techniques to detect overfitting in the model. Okay, so one more evaluation method. Do we have enough training samples? That is another dimension that we need to look at. When we train the model, we have to find out, did we train or did we have enough training samples? For that, scikit-learn also provides a function called learning curve. And essentially what learning curve is doing is it's going to take incrementally more number of samples gradually. Let's say you have 1,000 samples, and you're going to tell the learning curve that start with 10% of 1,000, then after that 20% of 1,000, 30% of 1,000, so on and so forth. So with the increasing number of samples, model is going to train with the data. Let's say 10% of 1,000, and then test it. Then 20% of the 1,000 train and test, and 30% of 1,000 train and test. And then we can measure the accuracies at each of the points, and then see how the curve looks like from the training and testing accuracy perspective. So that's called learning curve. With the increasing training data, add more training data, or it could be anything like images or text data. Plotting additional points. So with add a new point on the learning curve as you train and test it. As the training set size increases, the model accuracy generally should increase or should improve. And the accuracy and the validation should improve, might not improve as well, might decrease, and that will tell us the discrepancy or the gap between the training metric and the testing metric. So it's an iterative process. The learning curve is iterative, is going to use the data set in incremental manner and give you a plot, which is very easy to understand. Let's take a look at the learning curve demo in the Python code. So again, the load breast cancer and data and learning curve part of scikit-learn model selection. Load the data, train test split. And now I'm telling that, please divide the data incrementally in proportion, 10%, 32%, 55%, and so on and so forth. So basically you can mention this as an array, and I'm saying 10% and incrementally, is going to do, so 5 divisions you're mentioning, or you can do a hard-coded values also, but make sure they are between 0 and 1. It takes in terms of float or percentages. So you call learning curve and then the model X and Y and fold and training sizes. So first the model is going to take 10% of the data set, so 10% of X, and then divide that into, let's say, 5-fold, and then run the cross-validation score behind the scene and return the scores for each of the fold. And those things would be sitting in this variable. After that, we can plot the scores we can do a mean and standard deviation and then simply plot those. The plot will look like this generally, which is a happy case where the accuracies on the training and testing are pretty much in the same range, a very similar range, and also very high range. That means we don't need additional training data. But if it is like 90% and the testing is going below, that means there's something wrong. Probably we need additional samples. So utilize learning curve to validate the model, evaluate the model in terms of sufficiency of the training data. So that was the model evaluation process typically followed in machine learning. And in the next video, we'll talk about the hyperparameter optimization. How do we find the best combination or best settings for the KNN. Some of the parameters that we discussed: number of neighbors, the distance measure like Euclidean, Manhattan, Minkowski, and so on and so forth. Which measure is good for my data set? And the weights parameter, which is uniform and distance. So we will configure the tuning library and provide the range of data, and then we perform the optimization method, and it will return the best configuration that we should go with, uh, considering the data set and the model. Thanks for watching. See you in the next video.